Since we took a break from linear regression to cover cluster analysis, let's recap some important concepts of linear regression. So in linear regression, what we have is a set of predictor attributes and a target attribute, all of which are numeric attributes, either inherently numeric or converted to numeric. And what we are trying to do is to fit a linear function, okay, to fit a straight line or a hyperplane to fit these, to closely fit these values. Now, as we've already discussed, there's an infinite number of possibilities for how to fit the linear regression equation. But what we do is we try to fit that equation in which the predicted values are as close to the target values as possible. What do we mean by as close as possible? We take the deviation between the predicted value and the target value. That's the predicted value. This is the actual value. And we take the difference and square the difference and add up all of these squares. In other words, if we create a linear regression equation, that equation is going to make some predictions. Using that equation, we can make some predictions. Now, those predictions, of course, are not going to be exactly equal to the actual values. That would be utopian to think that that can happen. In a real scenario, that cannot happen. That is unlikely to happen. But what we are trying to do is to find that equation which gives the smallest value for this expression, right? Of course, each of these, yi minus yi hat is the predicted value, yi is the actual value. So each of these represents how far away the predicted value is from the actual value. And of course, we want the predicted values to be as close to the actual values as possible. So we take the sum of all of these, right? So we've got I, which is a particular value, and we add them all up. The sigma sign stands for adding it all up. So the total squared error is what this expression is. And what we are trying to do is to choose that model which minimizes this expression, which means obviously that the model we've built is in some sense closest to the actual values. And this criterion is what is called as the least squares criterion. And this is what linear regression uses. Let's take an example now. Let's say we've got a single predictor attribute called rooms, and we've got the target attribute called price, and we've got many points. And all we are showing is a single point. Let's say we've got information about 1,000 households. For each one, we've got the number of rooms and the price, right? So there are thousands of points here. But among those thousands of points, I've singled out just a single point. Okay, now suppose we are shown a random house, right? So we are told these are the prices of various homes, and here is a random home picked up from, which is compatible to this set of homes. What would be your prediction for the price of this home, right? We are not given any other information. We are only told that a random house has been selected. What is your prediction for the price of the home? Okay, so clearly in the absence of any other information, the best we can do is to make a naive prediction, which would be simply, well, my best bet is the average price of all the homes, right? That is what, if I am asked to do this repeatedly, I will come closest to the actual value overall if I keep predicting the average. Okay, so that's our prediction, which is what this line is, y bar, which is the average. So no matter which house we are given, we predict the average. But here is an actual house whose number of rooms is that much and whose price is that much, right? Number of rooms is where this would cut the x-axis. The price is where that would cut the y-axis. And its price happens to be actually lower than average. Okay, so now we ask the question, why is the price of this lower than average, right? And we are not told what, because we don't know the, number of rooms of this particular house. Of course, when we look at it on this chart, we do know the number of rooms, but in general, suppose I've said, well, I've picked a random house. What is your prediction? It is the average. And you say, no, you're wrong. It's not the average. It's actually below average. So what we want to do is to use regression to explain why the value of the house is what it is, below average, above average, equal to average, whatever. Okay, so now suppose we have got all the points and we have fitted a regression equation, and the regression equation looks like this. So now what happened is, earlier in the absence of the regression equation, our prediction error was y bar minus yi, because this point is xi yi. In the absence of the regression line, our error was the distance from this point all the way to that line, okay, which is yi minus y bar or y bar minus yi. Okay, depends on how you want to look at it. Okay, but with the regression line, we have now reduced the error to yi minus y hat being the predicted value. If you will recall from our prior discussion, our convention is to put a hat around predicted values. Okay, so the regression therefore managed to reduce the error from yi minus y bar to yi minus y hat, right? So that it reduced the error from this total amount to that amount. That's what the regression achieved. Okay. So now, in general, if you look at not just a single point, but all the points which are there in the regression, so what regression is trying to do is trying to explain the variability in the target attribute. Without the regression, we don't know why there is all that variation. With the regression is able to tell us, well, some houses have a price below the average because they are smaller houses, they have fewer rooms. Some houses have above average prices because they have more rooms. And therefore, regression is coming and telling us, you know what, the price is affected by the number of rooms. That is simple linear regression. In multiple linear regression, we are effectively going to say, well, the price is affected by so many different variables. Okay. However, the variability in the price is what we are interested in explaining, and therefore we need a measure of that variability. And of course, as we have discussed now many times, the measure of variability in a particular variable is nothing but the sum of squared deviations of that variable from the mean, right? So here's the mean. If all the values were exactly the same, then there is no variability because all of them are exactly the same. However, if the values start differing, then we measure the variability by taking the average and looking at the deviation of each value from the average. Okay, and in statistics, it's common practice to talk about squared deviations rather than just the raw deviations, right? So we've got the squared deviation. So for the ith value, the sum of the squared deviation is yi minus y hat, yi minus y bar squared. This is for the ith value. But then of course we don't have one value, we have n values, so we sum up from I equals 1 to n, and we get the total sum of the squared deviations from the mean. So this is called total sum of squares. Now we talk about how much of this variability is accounted for by the regression, and that is what is called sum of squared regression. And based on what we discussed in the previous slide, we know that regression is able to explain this much of the variability, y hat minus y bar. Okay, that is the distance between the regression equation and the mean. So that is the amount of variability which the regressionist says, yes, you should expect that, because the predictor attributes have certain values. Because of that, the target attribute is going to be lower by so much or higher by so much or exactly equal to the mean, etc. Okay, so that's what the sum of squared regressions is. Now the remaining is what remains unexplained, which is called the sum of squared errors. Okay, and that is yi minus y hat. Yi is the actual value, y hat is the predicted value. So the difference between the two, of course, is the error or the residual, and this represents the total of that. Okay, so now given all of these, it is always true that TSS is always equal to SSR plus SSE. Okay, so what we are effectively saying is this is the total variability. This is what the regression is able to explain. right? So therefore, the proportion of SSR as a proportion of TSS tells us about how much of the variation the regression is able to explain, and that is what is called as the R square, or coefficient of determination. That's a measure of how much of the variability in the target attribute is explained or accounted for by the regression. In the case of simple linear regression, R square is really the same thing as the square of the correlation coefficient. That just happens to be the case. Of course, that doesn't hold for multiple linear regression, because when you have multiple linear regression, you've got many predictor attributes. So you can't talk about a correlation coefficient, right? Because after all, a correlation coefficient only links two variables at a time. Okay. Then we also computed the root mean squared error. And basically the way in which we computed that is by looking at the errors, which is yi minus y hat. Yi is the actual value, y hat of I is the predicted value for that, corresponding to that value. And you add up the sum of squares of those, which is the total amount of errors. So you divide that by n, you get the amount of error per case, and you take the square root of that. That is what is called as the root mean squared error.